I'd like first thank you all for attending this talk, and also the organization committee for the room to present our research. So I'm Italo Assis. Today I'm talking about automatic workload scheduling for full waveform inversion in shared memory systems. This work is a cooperation between UFESA and the UFRN, which are two Brazilian universities. So on our agenda, we are going to briefly discuss one of the challenges of implementing full waveform inversion in shared memory systems. And then we're going to introduce you to our proposal, which is an auto-tuning for FWI using Patma library. Then we're going to see some results, mostly performance analysis, and finish with our conclusions. So full waveform inversion, I believe most of you here are familiar with. So I'm going to just tell how it works in a nutshell. So for an FWI, you basically take field data and an initial model, a poor initial model, and iteratively you optimize that model so that it gets closer to a true model, as we show here in figure 1. The main challenge on using FWI, because it's a time-consuming task, that's why we work to reduce its execution time. If we look close to an FWI outline, we're going to see that it has some main steps, mostly reading the input data, the observed data, initial data. Then we can compute a solution of a wave propagation, which we call the calculate data, for the initial model. Then we compute the objective function of FWI, as it is an optimization algorithm, and its gradient. And from that gradient, we can get to a new model. Then steps 3 to 6 can be repeated iteratively until we get to a predefined stop criterion. At least 2 of those steps involve computing the wave propagation, steps 3 and 5. That's why that task is compute intensive, and that's why we several works focus on reduce the execution time of the wave propagation. So let's let's look to a code snippet of a wave propagation. In general lines, it has a loop of time iterations, and inside of it we have nested loops for the spatial iterations. One of the techniques, or the HPC techniques used to reduce the time to execute the simulation, is using loop parallelization. And one of the main tools for doing that is OpenMP. So if we use OpenMP, we can use the directive, the Pragma MP4, and it's meant to divide the iterations over blocks and distribute those blocks over threads. If you want to optimize it, you can use the close schedule. As we can see on the code snippet, the close schedule has 2 arguments, the type and the chunk size. And the chunk size is basically the size of the blocks of iterations we're going to distribute, while the type is how we're going to distribute those blocks over the threads. The type can be static, meaning that we're going to distribute in round-robin fashion previously through the threads. And the dynamic is an on-demand distribution, meaning that when a thread is idle, it's going to take the next block to process. The guided type is basically the same of the dynamic, but the blocks start on bigger sizes, and then it's going to reduce over the time. The chunk size, the second parameter for schedule, is optional. If we don't set it, don't say the size of the blocks, then it's going to use the full PMP values, which are 1 if you use dynamic and guided, and it's the number of iterations over the number of threads if you use static. That leads to a decision. If you're a programmer and you want to optimize that code, you have to take the decision of either using the full OpenMP scheduler or define yourself the chunk size. If you use an OpenMP default scheduler, then that leads to our question if we are getting the best performance for the machine you're using and for the input size you are dealing with. On the other side, if you decide to define yourself the chunk size, and then we have the question, how can we do that? How can we optimize the chunk size? To address that issue, we propose using Patma. Patma is a library in C++. It's open source. It was developed on our project, and it's available on GitLab. You can have access through the QR code. And Patma stands for the parameter auto-tuning for shared memory algorithms. It's meant for interactive applications. So basically, the programmer can define which parameter he wants to optimize, and also the optimization method he wants to use. So let's make it a bit more clear here. The optimization method, the programmer can add its own optimization method, but we have two built-in methods on Patma, which are the neldermid, local optimizer, and also the coupled simulate annealing. Now, the coupled simulate annealing is basically multiple instances of simulate annealing. Simulate annealing involves two steps: the generation of results, of solutions, and the acceptance, and then all those instances of simulate annealing compared together to find a global optima. A detailed description of Patma is available. It's under reviews, but it's available on a preprint you can find online as well. So Patma has two operation modes. Both of them runs at execution time. The single iteration mode, the optimization will go on along with the process of your algorithm. So for each iteration of the algorithm, the optimizer will generate a solution and test the solution until it converges to a final solution. And from that point, the algorithm will continue without optimization. And also the entire execution mode, where we perform the initialization of the algorithm, we perform the whole optimization, get to a final optimized parameter, and then that final solution is used for the target method to run from the beginning. Okay, now that we know Patma, here's our proposal. We propose using FWI with Patma. How we do that? We use the entire execution mode because some of our previous works have shown that different iterations of the wave propagation has different costs. So we decided to take the first step of wave propagation as our target method. We do the whole optimization beforehand using couple simulated annealing. And after we have all of that is to optimize the chunk size for loop scheduling, as we saw before. And once we have an optimized chunk size, then we run the whole FWI using the chunk size we defined by optimization. We also defined some parameter. We can define on Patma some parameter limits. Here we chose to start on the chunk size on 50. That value is an empirical value found on previous works. Basically, it means that we don't want to use very small chunk size for dynamic scheduling because it has a high overhead management overhead. And the upper limit is the number of iterations over the threads, which means basically one block per thread. Our stop criteria is the number of iterations. Okay, going to our experiments, we wanted to compare our proposal method against OpenMP static and guided default schedulers. We didn't compare to the dynamic. As I said before, some of our previous works I show here have shown that dynamic default has very low performance for wave propagation because of management overhead. And we also want to compare our proposed method against dynamic, static, and guided schedulers using the chunk size as defined on the paper of Muhammad et al. In 2022. Over there, they define the chunk size as the formula you can see here. So basically, the chunk size is defined by based on the number of iterations and the number of threads. Here are the compute environments we use on our experiments. We try to use several kinds of compute environments, basically supercomputing nodes. We have 2 of them. We also have 2 virtual machines from Oracle Cloud and 1 bare metal machine for Oracle Cloud as well. As we can see, the processor architecture changes from one machine to another, and also the number of cores varies from 18 to 128. And typically, the L3 cache follows increases with the number of threads as well, as you can see in the last column. We also have different amounts of memory, which in our case means more or less computation because we use checkpoint, so we have to recompute the forward wave field. And we run our experiments in a code called Mamu. Mamu is also developed on our group. It's a C++ GitLab repository. You can find it online. It does perform 3D full waveform inversion and modeling. And here are some characteristics of our base code. It solves the acoustic wave equation through finite difference, 80th order on space, second order in time. It uses double precision for all data. We employed optimal checkpoint to reconstruct the forward wave field, and also using absorbing boundary conditions, basically a damping to absorb the energy at the borders. Our FWI parameters, we chose to try different input sizes. Here on figure 4, you can see the bigger model we used, with 400 grid points at each dimension. We generate other 2 input models by cutting the x dimensional half and 1/4. That leads to the 3 dimensions we have here. And we also use the Ariki source with peak frequency of 10 Hz. Time samples is 1 millisecond. Time steps 2,458, 10 meters of spatial resolution, and 25 grid points for the absorbing boundaries. As we chose to use the coupled simulate annealing, we also have to define its parameters, which are basically those 4. We took the values we chose from the literature. Firstly, we have the initial generation temperature, which we chose to be 100. The initial acceptance temperature is 0.9. The number of iterations is 40, and the number of optimizers, SA optimizers, is 4. Now let's have a look at the results. We performed 2 sets of experiments. This showcases the first set of experiments where we tried the 3 different input sizes on all the machines we talked before. Here we compare our proposed method against the full OpenMP static and guided. Figure A shows the comparison to static, where we can see that we have some speed up for all machines, ranging from 2% to 70%. And on figure B, we see the comparison with the guided OpenMP default scheduler. We also have some speed up here, vary from about 3% to 15%. And if you look at those 2 images, you can notice that, the computers here, the computer environments here are ordered by the number of cores. So as we increase the number of cores, you can see that we reach higher speed ups, which shows the scalability of our method. And this is the second set of experiments. Unfortunately, at that time, we didn't have access to Oracle Cloud resources. So we performed it on the 2 supercomputer nodes we have access to. This is for the first supercomputer, the Santos Dumont. Here we show the results for the 3 input sizes, letter I, B, and C, where we can see And we compare here in the second set of experiments, we compare also against the chunk size as proposed in Mohammed et al. In the literature. Here we can see that Mohammed et al. Reached slight speed up compared to the full OpenMP schedulers, and especially when it uses the dynamic scheduler. But still, our proposed method is about 5% faster for all the three scenarios here. In the second machine, the NPAD supercomputer, we can see that the formula from the literature seems not to adapt well to that machine, maybe because it's based on the number of iterations and threads, while we know that the chunk size may be affected for cache and system calls and many other factors. And here it has a worse result, even when compared to the full OpenMP. And still, our proposal has about 5% speed up when compared to the full OpenMP schedulers. Okay, so what I showed today was a strategy for an auto-tuning using Patma library to adjust the chunk size of loop scheduling in an FWI. From the experiments we run here, we could see that our proposed method performed both the OpenMP default schedulers and one method from the literature in all scenarios we tested in this research so far. The speedups reached from 2% up to 7%, depending on the number of cores, depending on the compute environment, and depending also the input size. For future work, actually the first topic is like an ongoing work. We are running the same experiments here on real data we have provided by our sponsor. And as future work, we plan to try auto-tuning other optimization parameters as well. This presentation I made here is fully described on a preprint paper. You can find it online. It's under revision as well. And to finish, I'd like to thank Shell Brazil for funding this research project, Oracle for Research for providing Oracle Cloud resources for our tests, and also the National Laboratory for Scientific Computing, LNCC in Brazil, and the High Performance Compute Center at UFRN and PAD, who provide us with supercomputing nodes facilities. Here we have the references we showed. You can skip these, and that's it for today. Thank you all.
Do we have any questions?
Hi, thank you, Italo, for the presentation and the work. What's the impact of the cache when you change the scheduling at the runtime between iterations? Because if you are changing the scheduling, you are changing where the data is. So what's the impact, and do you consider it in the evaluation?
Yeah, thanks for your question. I didn't talk about it in the presentation because of time constraints, but actually let me come back here to the chart. Okay, so actually when we compute when we measure the time of the target method on Patma, you can tell it that you want to skip any iterations. So on these experiments, we decided to skip the first iteration exactly because we wanted to avoid what we call cold start effects. So that we take like the second measurement time or the third measurement time where the cache is already started, and then we avoid those kind of effects.
That's good. Thank you very much.